So welcome to the first lecture of MCS 320. So the first lecture of the 8-week summer session. So this is a pre-recording for the first lecture. The course is Introduction to Symbolic Computation. I will present this in two parts. In the first part, I will use slides for the first 10 or 15 minutes or so to talk about the course and the discipline. In the second part of this presentation, I will transition into the Jupyter notebook. Okay, so what is this course? Let's go through it. So here is the catalog description. So it is a 3-credit hour course. We will introduce ourselves to Computer Algebra, Symbolic Computation, many mathematical algorithms, and we will see how to apply these algorithms. So what are the two prerequisites? So the first prerequisite is Calculus 3, which is at UIC Math 210, and the other prerequisite is computer literacy. So there are 4 courses listed here that may serve as a prerequisite for computer literacy. There is also consent of the instructor. If you have ever doubts whether this is the right course for you, whether you are prepared or not, please contact me. So this is the catalog with the prerequisites. Then this course is the first course in the computational track in the curriculum on mathematical computer science. So the second course is numerical analysis, which I will teach in fall, and then in spring I will teach introduction to industrial math and computation. So this is a course in the discipline. It's not a service course such as calculus, so this is a serious course. It is not a programming course, although we will use Python. So if you are unfamiliar with Python, you will pick up Python. So you will learn something about the programming language, but it is in essence a computational course. What's the difference? Well, in programming, we start from an algorithm and we end with a program that works. In a computational course, we start with a program that works, and then we ask what can we compute with this program. Okay, there are 3 goals that I have with this course. First, you have some understanding of symbolic computation already, but I hope this course deepens your understanding a little bit. This is also a hands-on course. So if you need to compute something, the natural reflex should be to reach for a computer algebra system, not for a sheet of paper. So the third goal is that you already know a lot of mathematics, but we can learn a lot more mathematics through computations. So I hope that it also kind of changes your perspective on how to learn mathematics. So this is what I have in mind, the lofty goals of this course. Then going to the nitty-gritty of the points, there will be 5 quizzes, 3 projects, 2 midterm exams, and 1 final exam. Breaking this up in 2 main parts, so there are quizzes and projects and homework, and then there are exams. So it kind of breaks up in 2 halves. Everything is online, so everything is hands-on, but there are parts on this course where you can take your time. That's with the quizzes, the projects, and the homework. While quizzes are actually still time limited, but there are more relaxed exercises, as I should say, and then there are the high-stakes exams. There are 700 points. You see that I do not list points for homework. Homework can make up for points lost. Typically, I will say 5 correct homework problems can make up for 1 missed quiz. When you are allowed to collaborate, it will explicitly state it so. Unless that is explicitly stated, then you should work individually. So we will be using Blackboard Collaborate for the online lectures, but I will distribute almost all material through the homepage for this course at the bottom of this slide. Okay, very good. I'm 5 minutes, 6 minutes in. So let us now get to the conceptual part. I should also say that at the bottom here of this slide, you find the detailed syllabus and the list of topics. So the course webpage is the main point for all information, main starting point for all information in this course. Okay, what is symbolic computation? What is computer algebra? Well, computer algebra is a subdiscipline of computer science that studies the algorithms for symbolic computation. So I have underlined the algorithms. Symbolic computation is computation with symbols rather than with numbers. So these are two definitions that help us to kind of give a focus of what are the topics in this course. This is a hands-on course. It's the first course in the computational track. So the main goal of this course is that it gives you the main tool to do computation with a computer. All right, what is the tool for computation that we will be using? We will be using SageMath and CoCalc. SageMath is a very large computer algebra system or a scientific software system that bundles many open source software packages. So in an earlier run of the course, we used Maple, but then we transitioned into SageMath. So why? Well, because it's free, and also as another aspect, it combines many packages that people actually use in research. ParisGP is used in number theory, Singular is used in computational algebraic geometry, GAP is used in group theory. And you see Python. Python is kind of the glue that combines the software systems. There's one reference, so I stole this picture of the car from the paper that is listed here. It contains the mission statement of the SAGE project. So note that there are two URLs. So there is the organization, the .org, which contains the free software package, and then there is the cloud service, the .com, which is the commercial service that is available for online execution. So this is a computational course. It's also a computer science course. Several of you who may be watching this are interested in software engineering. Well, I would say that SageMath is a very good example of a large software package that works, is free and open source. So to install this, there are binary installers. There you can also install it from source. Be mindful that even Sage is huge and it will require 1 gigabyte at least on your computer. Online execution does not require any installation. There are pros and cons with this. Okay, so what are we doing with symbolic computation in this course? The course is organized in 5 parts. So there are 2 midterm exams. The first midterm comes after parts 1 and 2. The second midterm comes after parts 3 and 4. There is a little bit of Julia in the last 2 lectures, mainly because Julia is a very exciting new development. So computer scientists come up with new languages very frequent and often. It does not happen often that there is a specific programming language specifically for scientific computing. I also hope to introduce a little bit about parallel computing in these last 2 lectures. This is a free course, free software, free lecture notes that I still developing that are posted at the course website. There is the Sage for undergraduates, and I happen to have a paper copy of the book which I flash out here, written by this professor here, who is kind enough to still make the PDF version of the book available on his website. So I have my own lecture notes that I follow, but I have found some inspiration in that textbook, so that's why I have to mention this. The textbook is also a good reference. If you are, so the course requires computer literacy, but if you're really on really shaky grounds with programming, and especially with Python, this reference also contains a very good introduction to Python. Of course, there are many other good introductions to Python, but this book is oriented to undergraduates in mathematics, in mathematical departments. So we are also all mathematical computer scientists, but we do have already some experience with computer literacy. Okay, so this almost concludes the first part of my presentation. So there is the Sage project, and then there is the Jupyter notebook. So both projects are separate. So in the second lecture, we'll be entirely on the Jupyter notebook. Here I mention it for its interface. So Jupyter is a web interface. It's the default web interface to SageMath. It's the interface to many other. So it stands for, it allows language agnostic computing, as they say. So we will be using the Jupyter notebook to document our computations. In the first lecture, I will just use mainly as a calculator. We will also be using it for plots. So one can use still everything on the terminal, but plots, that's often a little bit hard. What is important is that this is not a programming course, but we will need to document our computations. So it's a computational course, and often it's not so much important what is the number, but also that you can justify what the output really means. Okay, so this concludes the first portion of the lecture. So at this point in the class, I will break and ask if there are any questions. Here in this part, I will go to the web interface. So I have a browser open with several tabs. So when you start Jupyter, so here I'm doing this on a Windows computer. If you start Jupyter on your computer, if you have installed it, so I would actually say that this is still my preferred way of working. I like to have the software on my computers. So it has definitely an advantage. Note that if you start your Jupyter environment, you actually get you are somewhere on your disk, and here I have navigated to courses MCS 320 Summer 22 Lecture 01, and I have already a notebook sitting in there, and it's up and running. So in a way, you can follow the course by scrolling through notebooks that are posted on the course website. That's one way of going through the course. The disadvantage is that you should actually do it. So the computations that we will be doing in the remainder of the course are not that long. It's mainly important that you do this. So if there is not a work or a notebook there in the folder, then you can make a new one. So here I have two possible kernels, a Python 3 or SageMath 9.3. So at this point, so it's important that you click on the right kernel. So we will do that also in the CoCalc interface. So I can go to my existing worksheet, or I can click on a new kernel. So if I do that, then a new tab will come up, and then I have the first execution that I can do, the first cell that is there. I will do things many times and often. So let me go to the second way of working. So there is the SageMath cell server, which is a cloud service. It has the advantage if you need to do something quickly, you don't want to install in something. So I can type in a command and then I can evaluate. So this is the first symbolic computation that we have done in the course. So the SageMath cell server is very convenient if you want to do a very quick computation. You have your browser ready, you're connected to the internet, you see the URL here, and you type something. So Sage itself is quite huge, and that's perhaps an understatement, but the SageMath cell server gives you kind of a calculator that's available there for always. Okay, now the third way of doing this is the CoCalc. So CoCalc is a commercial spin-off from the SageMath project. There is no textbook for this course. And you can use CoCalc also for free. That's how I'm going to use it now. But perhaps I will recommend that if you are not installing CoCalc, if you do not install SageMath on your computer and use the convenience of CoCalc, I would suggest that you would consider buying a subscription. Okay, I will sign in. I have already made an account. It's also possible to do this without an account, but that is very unwise in the sense that you want your notebooks somewhere to be available. Okay, so you make an account. So I should say that the most important homework of this lecture is that either you install Sage on your computer, or perhaps also that you make an account on CoCalc, and that you make your first project or your first Jupyter notebook. Okay, I will go to projects, so I can go to projects also here. So I have already projects. I did this, I practiced this. I did this 2 hours ago, you can see. So I have a new project, but I have already a project sitting there. I will pretend that I haven't made it. So I will, for the purpose of illustration, I will create a new project. I start with the name of the course, the name of the lectures. You can pick any name, and I will create the project. Okay, so then I will start the project. Note that here is again my recommendation. So the subscription fees are actually not that high. The point being that if many people do the socially responsible thing, then the price keeps being low. You will, there are some warnings here. So the free account is free, but there are no guarantees. So be aware, again, the recommendation is that you will either install SageMath on your computer or do the prescription thing. Okay, I have now the beginning. Beginning is also always the hardest. So I clicked on new. So I have a project, which is my lecture. I have now a folder here. I'm probably not too good with names. So if you're not good with names, you see you get the date and but again, I will name it MCS 320 lecture 01. It is important that we click on a Jupyter notebook. And we have the math kernel. So I was on my Windows installation, I was using 9.3 because that has a convenient binary installer. So there are some notable changes along the way in the SageMath development process. So the last time when I taught this course, the interface language was Python 2 based. Now it's Python 3. There may be still differences, but I hope that the difference between 9.3 and 9.6 is not that high. Okay, so we will select the SageMath kernel. And now I can do my first symbolic computation. I can ask what is the sign of pi. So the block here where I've just typed this in is a cell, an execution cell, so it's with code. In the next lecture I will go over the difference between code cells and text cells. In this lecture we are working with code cells. And I will run this. So this will give 0 in due time. You see the advantage of using the Sage cell server for small computations. Let me take the opportunity. So there it is. So I can flip back to my original. So I started the kernel. So let's do this again. So you see I had my prepared, my set Jupyter notebook for this lecture, which I will post on the course website. And then I had the untitled, which I just did. So I made this with the new SageMath kernel. So, and here I have my untitled. So perhaps the untitled, so note that when we were teaching the course in earlier times, we were having explicitly always saying, please save your work, please save your work. Now people don't do that, of course, and there is an auto-saving that is happening. It's good to rename it. So otherwise, after 30 lectures, you have 30 untitled, Untitled 1, Untitled 2. So I will title my lectures to the MCS 320 lecture 0, and I will call it recording. In class, I will call it class. So this is the Jupyter notebook that I make during the recording. So I can do the symbolic computation again, but that seems a little bit tedious. So let me see pi, and I can also do pi with a capital P. And here you see that there is already a problem. So if you have taken a Python programming class, then you're no longer that scared of the exceptions that the system throws at you. But we have a name error, and the pi with a capital P is a name of a variable. The pi with little p is the symbolic constant pi. So I can verify this. It's a typed system. So I can ask what is the type of the pi that is in there. So it is a symbol. It is a symbolic expression. So symbolic computation is computing with symbols. A bit longer worded, it's computing with symbolic expressions. Okay, let me go back to the CoCalc. So I've done my symbolic computation. Let's go to the numerical world. So is this pi really pi? Well, depends what you understand with pi. I will compute a 20-digit approximation of pi. Okay, so let's ask what it is. Oops. Pi 20. And I can also ask for the type pi 20. Okay, so what do we see? We recognize the 3.1415, so fine. We see that we have 20. You can convert to a string and ask for the length. And now you see that if I'm asking for the type, that it is a number. It's a real number from MPFR. So MPFR, if you have a photographic memory from the first part of the lecture, MPFR was one of the wheels of the car. So in the first part of this course, we're looking more at the number systems. So here you see the number pi with 20 decimal places accuracy. Okay, let me flip back and forth. So I have my pi, my 20 decimal approximation for pi. I will compute it here again. So just in case if you would be following along, which I actually would recommend. It's rather tedious looking at somebody demonstrating, but it may be worthwhile if you are following along, and whenever things get too fast, you can always pause the recording. So we can see cells as execution blocks. It's part of a program, so you can type in multiple statements in a cell block. And I made a type error. So 20 is indeed an integer, but pi of 20 is a real number of the MPFR package. and the rings. So we will get to the rings at some point in the second week of this course. Okay, why do we actually use now this notebook? Well, it's a convenient web interface, but another convenience of the notebook is for plotting. So I can plot the sine function over minus pi. So see, it's auto-saving. I can make the plot. Just in case if you would have forgotten what is actually the sine function, well, here is the graph of the sine function. Okay, making sure that I can do this again and that my CoCalc is in sync. So what did we do so far? We did a symbolic computation, and now we are doing a plot. Visualization is very important in scientific computation, and in the second part of the course we will study visualizations and also animations. Here is one motivation for using the web interface. It provides us with a very convenient graphical user interface. Alright, so we can work with symbols, we can ask for numerical approximations, we can make plots. Now, the other part that I still want to show is, here I was indicating this MPFR. Where does this MPFR come from? One can ask Sage which system did the computation. So I will illustrate how this is done. So it's a special feature, so you have to import from the package miscellaneous of Sage, you have to import the citation module, and from that we import the get systems. So if you have done Python, then Python is modular, so we can import modules. Here I'm importing one specific function out of a package. So when I did pi.n digits equals 20, which system did actually execute this? Let's see this. Oops, there is some red coming up. So this is my installation. It's a binary installation. Let's see, I'm now curious if I get this also in the cloud. So there are some advantages of running things in the cloud as well. Some advantages in the sense that you would hope that everything works in the way it's supposed to work. Well, it did actually work in the way it works. So it gave me MPFR, and it also gave me the other system, JINAC. So this is a Python. One can see this is a Python based system. Sage is the system that is built on top of many other systems. So if one is using certain features of Sage, it's often very good also to be aware what are the underlying packages that execute everything. Okay, so let me, for the sake of demonstrating everything twice, let me go back to the CoCalc environment and run exactly the same commands. So we were asking to see a numerical approximation of pi with 20 decimal places. And I made a mistake by forgetting the quotes. So you see, making this mistake has some benefits. Again, the mistakes, so I get actually the same user warning here. We will get into code generation later, so that might be now a little bit that causes me worry. But notice that the exception handling mechanism essentially provides you with feedback. Okay, so looking at the exceptions, you see the exception is raised. So in a way, you would expect from commercial systems a little bit a nicer and a more politer, more less technical. But you see we got a type error, and you see that the command that is raised, the command must be a string. So I knew it too late when I had typed it in, that here I had to put whatever I want to ask the command for. I will have to put it around quotes or double quotes. I'll rerun this. Okay, and I got the same answer. So 9.6, 9.3 on Windows, 9.3 in the cloud, 9.6. Okay, I've executed about 7 statements at this point. Let me go back to the first worksheet that I had. You see, I said that I executed 7, but I made some mistakes here. So I had a mistake that I made also here. So this is 3 and 4. So this, the thing that I want to illustrate is that often it's very good to redo. So if I want to clean up my worksheet a little bit, so this will give a name error. So I will comment this out. So in Python, this is the symbol for comment. So this will give a name error, because pi is a name of a variable and not assigned yet, so it's a free variable name. So it's not defined yet. So why do I do this? Because the feature that I would like to illustrate now is that you can clear all the output, or you can also restart. So this will remove all the output. So all the work that you have been doing and all the experimentation, the mistakes that are in there, you kind of polish things up. And then you can, so the kernel is restarting now. And this is also for me a good way to save. So it's auto-saved, but I save and checkpoint. And then I can do cell and run all. Here it's rather a very, very small computation, small notebook, but still it's very good practice that your notebook runs from top to bottom, just like you would run a program. Now the notebook has the advantage that you can execute your cells in any order. This has a lot of flexibility. But when you are working on a project, before you hand in, or in a list of exercises, before you hand in, it's good to actually clean things up a little bit. Okay, I'm at 40 minutes and I don't want to take much more time. I want to solve a problem now. So here is the problem that I want to solve. So the problem that I want to solve, here it is. Oops, I inadvertently actually went through the prepared worksheet. Very good. So let me illustrate how you can copy and paste. So I can use the copy feature and go to my other worksheet and then try to paste. There we go. So that's another good feature. So you can have multiple notebooks open at the same time and pick from whatever you feel is necessary. So this is pedagogically extremely bad because I was actually only intending to show the problem first. So we know that pi is a transcendental number. We can never fully represent it completely with all its decimal places. It goes on forever. But we can make rational approximations. So here you see the statement. We compute a floating point approximation, and then from the floating point approximation we go to a rational approximation. Okay, so let me pretend again, and then I can execute this. So I will go through this a little bit more slowly, but here is the answer. There are many things that I need to explain. So there is the list comprehension from Python. You see the for loop, but the for loop is in between a square bracket. So the square bracket is the notation for a list. So a for loop creates a list. So you can, if you took a traditional programming language, you may have been introduced to a for loop to make a sequence of numbers that you then store in a list. You can turn it the other way around. You can make a list saying what you want to make. So here we have the statement that we repeat, where the k is a parameter. And the k, the index of the parameter, runs through the range, here running from 1 to 10. So the range here starts at 1, but it ends at 11 minus 1. And here you see all the different rational approximations of pi, from 1 decimal place accurate to 10 decimal places accurate. These are not the consecutive rational approximations for pi. We can get to that later. So these are the approximations that are guaranteed an accuracy of the prescribed decimal places. Okay, so this is one way of explaining this, a very bad way, for first saying the problem and then the answer right away. Let me do this a little bit now more pedagogically justified. So we have seen how to go from a rational, from a symbol for pi to pi 20, which was the 20 decimal representation. So this gives me pi 20 is not defined, and indeed pi 20 should have been with a lowercase p. So here I have my 20 decimal places for pi. I can ask for the rational approximation for that number. So this will convert QQ, Q, the letter Q, the fancy letter Q often, is the symbol that the mathematicians use for the rational field. So QQ converts any floating point number to the nearest rational number. So if I would go back, so I can go back and forward. So let me make a new code cell. Okay, so here is one of the moments where the web interface is testing my patience. So I will insert a cell below or above. I have the QQP20, so that is my rational approximation. So QP20, let's give it a name, QQ20. Okay, so here we go. So I have my QPy20, my rational number. And what I actually want to show is how you can go back to the real numbers. So we have RR in analogy with the QQ. And the RR is by default the double precision floating point numbers. So I would need to use the real field with 20 decimal places. But you get the point. So you can go from the floating point approximations to the rational approximations. So let me try to explain what I was trying to do on the other worksheet. So I was wanting to have a sequence of approximations. So I'm going to add a cell below. So let me indicate again the problem. So the problem is to compute a sequence of approximations for pi, and that accurate to from 1 to 10 decimal places. So I need a sequence of numbers from 1 to 10. So here is how you can play with the list comprehensions. This is not the best way to make a list comprehension, but you can see how I'm going to make up my answer. So I have pi.n digits equals k. And here I have my sequence of floating point approximations. Each time I gain 1 decimal place of pi. And what I wanted to compute were the rational approximations. And here is the answer. Okay, so this was the last technical issue that I wanted to show. I'm in 49 minutes. So I will stop this recording right soon. What is the main important point is that we understand that symbolic computation is computing with symbols. Computer algebra studies the algorithms for symbolic computation. With SageMath, we have our computer algebra system, our free computer algebra system that will be used throughout this course. The Jupyter notebook is the web interface. We can use this in the cloud for free, or we can install SageMath on our computer. So I thank you for watching.